Well, welcome back, everyone. We'll get started in just a few moments. Well, it looks like we can start. Welcome back, folks. I'm glad that at least you two have made it today. It looks like it's a pretty small class, but we'll still make it work. For the big announcement is we have our third upcoming exam, which is going to be next Monday. For the online section, I don't think anyone's here from the online section today, but nonetheless, we'll say it anyways. Please make sure to schedule your exam as soon as possible. And for the in-person section, that's us today, we'll have the exam as normal in the classroom. So we'll meet on Monday during ordinary class time. And that means for the online section, when you see this video later on, we won't have class on Monday, but we'll be back to class as normal on Wednesday of that week. The exam is going to be short, even shorter than the normal exams we've done on exam 1 and exam 2. It's just going to be 3 questions from these specific chapters. Question 1 is going to be a difference of population means. So this one is either going to be a hypothesis test or a confidence interval. Question 2, if we chose a hypothesis test, that one will be a confidence interval, and vice versa. This is from one population proportion. And the third question from chapter 20, just so that we're not going right up against the last remaining time, we gave a hint on our Monday's class that the chapter 20 question will specifically be a confidence interval problem. So those are basically the comments we made on last Monday. And as far as the materials for the exam, the formula sheet will be attached as the real last page of the exam. So definitely take a look into that as you're studying the exam, just to orient yourself with where all the information is. And so for additional problems to practice, we can take a look at these practice exams. But getting caught up in the homework sets for these 3 chapters, again, is probably the best place to start for preparing for the exam. Well, any questions or comments at all, folks, before we get started today? Okay, well, let's jump back in. We are nearly completing the chapter 20, handling 2 proportions. Once we conclude on this chapter, we'll move over to the chi-squared goodness of fit test. So here is where we left off on the end of Wednesday's class. We did a prior example right before getting to this spot, which was essentially to introduce the pooled sample proportion and to do a derivation that shows what a new standard error is going to look like. So this is the entire write-up for our new hypothesis test. The idea is, if we're testing this null hypothesis that P1 is equal to P2, we're making a pretty big assumption about the 2 independent populations. We're assuming they are identical with respect to those 2 parameters. And if those parameters are identical, when we went to take the 2 independent samples, we are really sampling from the same effective population. By that logic, we pool the proportion of successes. We add the number of successes, we add the total sample size, and this one statistic p hat is approximating P1, which we are assuming is equaling P2, which is some common value P naught, which is going to be all approximately equal to the pooled sample proportion of successes. Then the next thing we did is we went into the central limit theorem at the very top of these notes that we derived, and we made this assumption if P1 is equal to P2, which is equal to P naught. P naught is an unknown, but we will calculate P hat through the actual sample data, and our standard error comes out in this format. After doing a little bit of simplification, it's a brand new structure, and the big warning is only use this for hypothesis tests. In other words, if you're doing a confidence interval in this chapter, then the standard error takes a totally different format. So we have to be very cautious about that. Well, any last questions at all, folks, with the introduction to this new test statistic? Okay, well, as far as the conditions go, they're pretty similar, except, excuse me, part two does take a different format. Part one, we'll briefly discuss based off what we see from the context of the problem itself. We need to discuss if this is really two independent populations. And if we have a random sample, a simple random sample being the gold standard from both of those two populations. Condition three, same as what we've seen in chapter 19. Here we'll briefly discuss if we believe or if we believe against the idea that the population is at least 10 times as large as the respective sample for both populations and both samples. So those are just two things that we briefly talk about based off whatever the context tells us about the problem. And for condition two, we carefully check. Showing the specific counts in the problem that we're working on. Showing the counts just for the sake of full credit on that problem. And notice that this one is quite a bit different. If you're thinking about what we did in chapter 19, we assumed the null hypothesis was true, but we put in a value for P1 itself. Once we had a value for the one and only parameter, we could calculate the expected number of successes, the expected number of failures using that value from the parameter. But we can't do that in this chapter. This time, we're only assuming that they're directly equal, but we're not making an assumption on what the common value P naught is whatsoever in this particular procedure. So because P naught is an unknown in this problem, we can't calculate the expected number of successes and failures. So we just go back to what we see in the sample. Within the sample itself, we have to have at least 5 successes, 5 failures in the first sample, and same 5 successes, 5 failures in the second sample. If that benchmark is met, we consider the central limit theorem to be accurate enough to give us a accurate p-value. So putting that all together, that's our test statistic Z. It measures if the null hypothesis is true, how far away are the sample proportion of successes in terms of the standard error, which is an approximate standard deviation. Once we have that test statistic, we compute the p-value as before. I did make some changes here on the document. Here I just had F, but it's a better practice in RStudio to just type out false in all uppercase. So I made a correction there. And in my original notes, again, sorry if you already printed these out, I had 2 versions of ways to calculate the p-value, if the test statistic is positive or if it's negative. But I felt that was kind of weird because we did it a particular way in chapters 14, 15, and 19. So this change here is just to make it similar to the way we've indicate our p-value for the two-tail test and all previous of those chapters. So sorry for that last bigger change right here. This just makes it more parallel to what we've been doing all along. So the change is I put absolute value Z here, and that means we only have to state this formula once to get the p-value. And same big warning that we mentioned before, if you're doing the two-tail test, which is a common test, it's the default one for hypothesis testing. Don't forget you have to multiply by 2. So let's write that out as a fast comment. Do not forget to multiply by 2. If we do not multiply by 2, it means we're getting a p-value more in line with either a right tail test or a left tail test, which was not our intention originally. Okay, well, that's the full write-up. We have the test statistic description, the new standard error, and really the p-values here. We've done these before. I didn't put in the curve for the normal distribution because we get the idea. This is just our really 4th chart looking at the same kind of structure. Any questions or comments at all, folks, before we run this through a brand new example? Okay, well, let's give this a try. Here's our new context down below to work the problem through. First, there's a bit of overall context. Then down below, the next paragraph is the specific study that we're looking into. The context here says corals, like in the ocean, share a symbiotic relationship with microscopic algae called zooxanthellae. I'm not going to be able to pronounce that. Called that right there, however that's pronounced. These algae live directly within the coral's tissue, and that's what gives it its vibrant color, as well as provides up to 90% of the coral's energy through photosynthesis. So this is a very direct symbiotic relationship. But when things go wrong, when there's something happening with the ocean, maybe it's acidification, rising temperatures of the ocean, when anything happens that stresses out the corals, they expel the algae and they become completely white, which is pretty stark. If you compare what the coral reef originally looked like versus a bleached colony, the phenomenon is called bleaching because of that total white appearance they take on. So that's the biology of the problem so far. And here's where the study actually gets going. Marine biologists are studying the effects of warming ocean temperatures on two independent coral reef systems. And those are good words there. That tells us we really have two independent populations. They want to know if there's a significant difference at the 1% significance level. Well, they gave us two values there. Alpha is 0.01. And when they said significant difference, well, we're running this through a hypothesis test, and they didn't ask for a greater than or less than. They're just asking for a not equals. This one is a two-tailed test by those highlighted words there. So we want to know the difference between two independent populations in the proportion of corals experiencing bleaching. From these words here, this is telling us the study is concerned about bleaching of the corals. So that's the success in the problem. Even though the success is not a good thing, this is a bad outcome for the ecosystem. That's what we're studying. So this is our success. The corals become bleached, and the two independent coral reef systems are going to be the Great Barrier Reef in Australia and the Mesoamerican Barrier Reef in the Caribbean. So we have two populations we're concerned with. It goes on to say, out of the 250 corals from the Great Barrier Reef, the first population, we have 45 successes. 45 showed signs of bleaching. And likewise, out of the 300 corals sampled in the Mesoamerican Barrier Reef, 72 showed sign of bleaching. So 72 successes there. So that's the readout of the problem so far. And usually when you have two independent populations like these, there's two sample sizes, there's two sets of successes. Sometimes it's a good idea to take a little bit extra time, say in the margin, or let's include a little bit of space here just to organize our data as we see it. So first, for the Great Barrier Reef, we know this is in Australia, so I'll just refer to that population this way. We had X1 in our notation, uppercase X, starting in chapter 19, means the number of successes, which was 45. So X1 is 45. The sample size N1, this was a sample of 250 corals. You have to get that information right. So right here, N1 is 250. So that takes care of one sample. The next population, Mesoamerican Barrier Reef. And here we had, in the Mesoamerican Barrier Reef, 72 successes. So X2 is 72. The sample size is larger. It's at 300 corals sampled in this population. So those are our two sets of values. The overall statistics that we'll measure are p hat 1, 45 out of 250, and p hat 2, 72 out of 300. So that's really the same thing the context told us, but writing it down by hand like this, again, either in the margin of the paper, include a little additional space, is a good practice just to kind of think about the context again and internalize it. Well, we're about ready to run through the procedure, and it's the same kind of song and dance we've done for so many other hypothesis tests. We don't want to know exactly what the parameters are in context, say exactly what the hypotheses are in terms of the parameters, check conditions, and then get to the math part of the problem. Any questions at all, folks, before we get going? Okay, let's kickstart this. There are two populations, categorical variables been measured, a success, bleached corals, a failure, non-bleached corals. P without a hat is going to be the true population proportion successes, but that means it's the parameter. So we can now say let P1 approximated by that P hat 1 and P2 approximated by that P hat 2 be the true proportion. It's proportion of successes, but we have to say in context what the success was, bleached corals. So let's say the true proportion of all corals that are bleached. Now we have to mention the populations, and there's two. You have to say what population each parameter P1, P2 belongs to. So we'll start here, Great Barrier Reef that are bleached in the Great Barrier Reef, and other population, Mesoamerican Barrier Reef, respectively. So there they are. We have two parameters down on paper, pretty much defined in the same kind of way we did the confidence interval problem, and extremely analogous to what we did in chapter 20, chapter 19, other than now there's two population proportions of successes. Any questions at the moment, folks? Writing down parameters? Okay, once we have parameters down, next level of work is null alternative hypothesis. The null is H naught. And whether you're in, say, chapter 18 or chapter 20, you've noticed that our null hypothesis takes on essentially one form. The null is that P1 equals P2. We make an assumption that there is no difference between the populations. We test this against the assumption, the actual research hypothesis. They want to know if there's significant difference between them. So we form HA, the statement that P1 is not equal to P2. We're using the two-tailed test again, so the not equal direction goes here. And we'll test this at alpha at 0.01. So that's our benchmark for enough evidence to reject the null hypothesis and make a conclusion we have significant statistical evidence. The alternative right there is true. So that's our null alternative, pretty much the same format of what we did in chapter 18. Only difference is these are P's instead of mu's. The data is categorical instead of quantitative. The next stop is checking conditions. We probably need a little bit more space for that. As far as the condition checking goes, condition 1 is not just about randomization. We need to know that we have two independent samples in the first place. We have a sample coming from the barrier reef, coming from a Mesoamerican barrier reef, and really you just said straight out it's independent, so that qualifies. This fits the right procedure. We can say the samples came from two independent populations. So that part's met. The next part we look for is read through the context again and look for information about randomization. Well, this is a pretty brief context. They didn't tell us how they got these corals. Randomly selecting corals as a simple random sample sounds like it'd be a very involved process, but marine biologists, if they're working really hard with statisticians, they can take a random representative sample of corals in these two different reefs. But we weren't told anything about that. We just were told that out of 250 corals from the first population, out of 300 corals in the second population, sampled, but no information on random sampling. So lacking that information, we'll make a statement here. There is no information about the samples being random. Does that mean they are absolutely non-random? No, it just didn't give us enough information on how they got the sample. If there was more information in this context that told us they went to the Great Barrier Reef, parked a boat, sent a dive team out, and just counted the first 250 corals nearby that boat, we would have said that's not a random sample. That's a convenient sample. They just went to a spot and counted all the corals right next to that one location. So if they said that in the problem, we would say not a simple random sample at all. These data don't meet the condition. But with the very, very limited context we were given, we don't know how they got that sample. So it might have been random, it might have been representative, it might not have been. We'll just state what we know, and what we know is no information given whatsoever. Kind of frustrating sometimes when these problems don't really say much about the sampling design. Well, any questions with that first part of the conditions? Okay, well, the next part is our sample size large enough? We count the number of successes in the sample. Again, stark contrast from what we did in chapter 19. And the counts that we're looking for are very different once you look into chapter 19 versus chapter 20 versus chapter 21. So a really good idea, once you decide what procedure you're running, go to that particular chapter, look up the procedure. Usually there's a write-up page, so it's really brief. You don't have to scroll through everything we wrote down in chapter 20. This is the fast write-up page that shows you the information a little bit more fast in one spot. And double check those counts because it's easy to get mixed up with the different values that are placed. For this particular hypothesis test, we want at least 5 successes and failures in both samples. So we go back to our data. Great Barrier Reef. From that population, it had 45 successes, which is greater than or equal to 5. That's our benchmark for having a large enough sample size. Successes. If there's 45 successes in a sample of 250, that means there's 205, which is greater than or equal to 5 failures. So we meet the requirements on that sample, and definitely on this one as well, right? The sample size is larger, the number of successes is larger. So let's just write this out just to get it down on paper. For the Mesoamerican Barrier Reef, we have 72 greater than or equal to 5 successes. And sample size is 300, so that would imply 228 greater than or equal to 5 failures. So I'm writing greater than or equal to 5, just as a reminder, that's the condition we had to pass on all 4 of those counts. Be sure to show these counts specifically, 45, 72, 205, 228 on homework assignments. And when we do this on the final exam, you'll need to show those counts as well. So here, with all of these conditions passing, we can say the sample size is large enough. It's not the whole story because just like we mentioned in chapter 19, And as well as this chapter for the confidence interval, the entire procedure can fall flat on its face. The central limit theorem can fail if you sample too high. That's kind of weird in a way. It has to be large enough to pass all these four conditions here. But if it's too large, we have a different kind of problem with the central limit theorem breaking down. Our benchmark was always that the sample we pull, when we think about the population size, the population should be at least 10 times as big as those two samples here. But if we're talking about corals in the Great Barrier Reef or the Mesoamerican Barrier Reef, there are millions of corals, if not billions. I'd say millions to around a range of 100 millions is appropriate. So these samples are very, very minuscule. So let's just make an overall statement. The populations are in the millions. And so much larger than 10 times the samples. Here we used information about just the ecology of what's going on in the Great Barrier Reef, the Mesoamerican Barrier Reef. Sometimes it's not as easy to resolve this. So when it says in the conditions, briefly discuss just based on what you know, you don't have to make any big statements that involves lots of research. Just go by what you can determine by the information in the problem. And if you justify it based on what you know, you can't really lose points on that question. Well, we've done all the hard work just thinking about the core context itself, writing down the parameters, the hypothesis test, checking conditions. Beyond this, it's all math using these numbers that we indicated here after the main context. Any questions at all, folks, before we go to the computational side? Okay, I always feel like this part goes a little bit faster, but the formulas are different, so we'll do this part with care as always. First thing we want to compute is the pooled sample proportion of successes. And be really careful with this one. You know, one thought you might have had is, this is the proportion of successes in the first sample. This is the proportion of successes in the second sample, but you cannot actually add those together. That would give you a totally incorrect statistic. So let's write down this formula carefully. The correct value is going to be p hat. That's the symbol for the pooled proportion of successes. Its formula is x1 plus x2 divided by n1 plus n2. And observe, absolutely not the same thing as adding both of these fractions together, because that's not a common denominator at all. That's a whole new formula. So the successes went 45 plus 72. The samples are 250 plus 300. So we get 550 in the denominator. And let me use a calculator for the numerator. 45 plus 72 for 117 in the numerator. And that does the job in part D. So once we have the sample proportion of successes, we can move on to the next level, get a standard error. Any questions on that computation there? Okay, and just reviewing the logic of what we're doing so far, to get a p-value, we assume that null hypothesis right here at the top is true. And if it's true, we're regarding our two populations as being essentially the same with respect to coral bleaching. So this is equal to some unknown value, and p hat is the estimator for it. Then in the central limit theorem, the standard deviation for p hat 1 minus p hat 2 is given this way. Well, rather, the standard deviation is given in a particular way, and its approximation is what I should have said. Its standard error is given in this format. Standard error of p hat 1 minus p hat 2, excuse me, that's just p hat, referring to the p hat right above. Standard error of the statistic p hat is going to be the square root of p hat times 1 minus p hat times 1 over n1 plus 1 over n2. So that's the formula that we were deriving in example 3, citing the central limit theorem and tracking changes after assuming a null hypothesis up here is true. Once we have that formula down, we just plug in values. This is going to be the square root of, use this value from the prior step, 117, over 550, 1 minus 117, over 550, multiply by 1 over the sample sizes, so 1 over 250, plus 1 over 300 coming from the second sample. So there it is in its full glory, just a new standard error. And maybe just another reminder as far as exam 3 goes, whichever formula that you're using, whether it's a standard error, a test statistic, confidence interval, degrees of freedom, and so on, if you put down on paper something like this, no matter what goes wrong in the calculator, I give a lot of partial credit for just putting the information together like that. So this is like insurance on making a silly calculator mistake when you really know the concept. Be sure to show that on paper. Then to compute it, I'll just use this as the calculator. Go SQRT or practice in your scientific calculator as well that you intend to bring to the exam. It's 117 over 550 times 1 minus the same value times 1 over 250 plus 1 over 300. And that's our standard error. So let's pull this in, 0.035045 upon rounding. And let me double check my numbers as usual, 0.35045. Okay, I think I've got it. So that standard error, once again, is the approximate standard deviation of the sampling distribution right here, p hat 1 minus p hat 2, under the assumption the null hypothesis is true, changing the format of that portion right there. So we approximated that standard deviation. We've got a number down, and now we can calculate the test statistic on the very next step. So following how our formulas go, the test statistic is computed in this way. We take z equals p hat 1 minus p hat 2, divide by the standard error of p hat. And now there's really 3 statistics on paper. There's the sample proportion of successes, p hat 1, p hat 2 from the first and second sample. There's the pooled sample proportion of successes up at the very top here, whose sole purpose was to give us the standard error. So keep in mind, we have to be really careful as we track all these different values. So on the very first step, plug in the p hats that we calculated at the start of the problem. 45 over 250 minus 72 over 300. Divided by the approximate standard deviation, 0.035045. So we've just about got it. The whole purpose of this test statistic now is to address the question, if you're assuming this null hypothesis way up here is actually true, how many standard deviations are your 2 statistics away from each other? If it's a lot of standard deviations, it's giving us evidence that that was a false assumption in the very first place. And we're going to determine what's a lot of standard deviations based upon a p-value and the significance level alpha right up here on the top as well. So this is the exciting part of the problem. We're nearly ready to get a p-value, and this gives us number of standard deviations approximately. But at the end of the day, it's just another calculator operation. Be careful with order of operations. You need a parenthesis for the numerator, 45 over 250 minus 72 over 300. Divide by the prior step value, 0.035045. And that's our number of standard deviations, making it kind of borderline in a certain sense. It's almost 2 standard deviations, and sometimes you get significance around 2 standard deviations, especially if it's a left tail test or a right tail test. The ours is two-tailed, which means the p-value is doubled from a left tail or right tail test. So we might not have statistical significance, but we still have to work it out. Negative 1.7121. Double checking on the rounding there. Okay, I think we've got it. That's our number of standard deviations that the sample data is away from each other approximately. From there, we can get a p-value. And after that, the problem is essentially done. We just need a practical conclusion to our hypotheses we stated. So here's how the p-value goes. I don't think we actually need the sample data here any longer. Let's chuck it. P-value. Following the syntax we wrote in the formula above this example would be calculated this way. 2 times p norm. I'll keep it in the exact format where I'm going to put in absolute value of z. But if you just took the absolute value and plugged in the positive number, that works just as well. So I'll write ABS, negative 1.7121. And you need to put in next lower dot tail equals false. Again, this is pretty much how the formula was cited. All I've done is put in a value for z. And if you just force that positive, you can drop the absolute value part here. So I wrote it this way just to make it parallel to how we stated it in the notes. We've done a lot of these p-norm functions starting all the way back in chapter 11. I think that was on like week 2 or week 3. So it's just another one along those lines. But don't forget the 2 times. So 2 times p-norm, absolute value, negative 1.7121, lower dot tail equals false. And this is what we get. Very commonly round to 4 decimal places for both the test statistic and the p-value. And this one is going to be at 0.0869. Okay, I think I've got those digits in, rounded it correctly. Well, at 0.0869, we need to determine what our conclusion is going to be, but any questions or comments at all, folks, to this stage? Okay, at this stage, this is where your eyes would want to go to the very top of the document. For me, I have to scroll all the way to the top. Let's grab our original statements of the parameters and our original hypotheses, as well as the significance level. So almost negative 2 standard deviations, 1.71 negative. Turns out it wasn't a lot. That p-value, you know, it might have been significant if the significance level alpha was at 0.10, and that is an appropriate significance level alpha to set. It means your type 1 error is 10%, pretty huge. This one wanted to minimize type 1 error, so it's at 1% instead, which means we do not have significant statistical significance whatsoever. But keep in mind that if researchers were doing this problem, and for some reason they really wanted statistical significance and did this after they collect the data, ran the numbers, that would be one of the most unethical things ever to do. Once you state these hypotheses, it's done before you even collect the data whatsoever. And once you run the data through the procedure you've chosen, once you know that it meets the conditions, we can never change the significance level alpha. This is set in stone. And if we do change it to try to force statistical significance, we mentioned in chapter 15, that whole thing is called p-hacking. And it's a very unsavory way to be unethical with statistics. So this has to stay exactly where it is, no matter how heartbreaking it might be that we didn't get statistical significance. So now let's write down our ultimate conclusion. Or maybe let's put down what we usually put in on paper. Just a quick comment, the p-value, 0.0869. let me try my decimals here, 0.0869 is greater than or equal to 0.01, which is alpha, or equal to, because even if it was somehow miraculously directly equal to 0.01, we still fail to reject. So I put it in that way as a reminder. This means fail to reject H naught. But this is not how the study would be phrased. The way it would be phrased is they go back here. That was the research question. So the way they're going to give a conclusion now is they're going to be honest and say, we did not have significant statistical evidence that that statement is true. So that's how we phrase the conclusion. We don't say we fail to reject the null hypothesis. We say what it means if we fail to reject the null hypothesis, always focusing on the alternative in our conclusions. So we'll do the same on exam questions as well, say on the third exam as well as the final exam, and write it out this way. This study fails to provide the failure coming from right here. It's greater than alpha in the p-value, significant statistical evidence, and I'll say in parenthetical what our level was at the 1% significance level. That, then we return to our alternative hypothesis. We didn't find evidence that that's true. So the rate of coral bleaching, we don't have evidence of a difference. It doesn't mean we have evidence that they're the same. It just means we didn't detect a difference whatsoever. So we'll have to say that out just as we see it. Writing up the parameters again in this format, we can say that the true proportion of all corals that are bleached in the Great Barrier Reef and in the Mesoamerican Barrier Reef are different. And once again, the one conclusion we have to absolutely avoid is conveying anything along the lines of saying we have evidence that they're the same. That's the one sad side effect about hypothesis testing. It does not give evidence that the null hypothesis is true. The whole procedure is done by assuming it's true in the first place and seeing how close or how far apart our data is under that assumption through that test statistic. So that's the one and only conclusion we can give. By failing to find statistical significant evidence would read out a conclusion in that kind of way. Well, we did, folks. That's the top to bottom procedure for the difference between two population proportions, where there's exactly two outcomes, successes and failures. Any last questions or thoughts at all, folks, getting through this chapter 20? Okay, well, congratulations on getting through it. For our next stop on our way of collecting statistical procedures, we're going to take a look into categorical data again before returning back to quantitative data in the ANOVA procedure. So what we're doing this time is, sorry, wrong document. We were just here, two categorical variables. The first variable says, which population are you in? The Great Barrier Reef or the Mesoamerican Barrier Reef. The other categorical variable was just to say what happened to each individual in the sample. Was it a success, bleached coral, or a failure, a non-bleached coral? But there's a lot more we could talk about with categorical data. And so we're going into this situation. This chapter 21 on the chi-squared test for goodness of fit will feel a little bit like chapter 19. The only one and only difference that we have, though, is this time we're going to say there are more than two outcomes and see just how that method's going to change. We need a whole different kind of test statistic, and in fact, a whole different kind of probability model to work with once we make the assumption our one categorical variable has, say, 3 outcomes, 5 outcomes, or so on. So let's take a look at how that goes. And here is the finally, the so-called chi-square test for goodness of fit. First page on the document is just orienting us into what the new probability model even is in the first place. When we say chi-square, we're talking about a specific probability model, just like the normal distribution or say like the t-distribution. It's got a definition here, but this is really here mostly for the sake of convenience more than anything. So if you want to actually define the probability density function for the chi-squared model, it's this, a pretty complicated mathematical structure. K minus 1 has to be a positive integer. It's referred to as the degrees of freedom. But already that gives us some interesting information in this new landscape. K is going to be the number of outcomes. And here we have one categorical variable like we mentioned, but we're always going to assume in chapter 21, if we're running this chi-square test, K, the number of outcomes of our variable, is greater than 2, or greater than or equal to 3, if you prefer to say it that way. So once we know the number of outcomes, it determines K minus 1, that's the degrees of freedom in the problem. And once you determine K, you have a particular shape of the chi-square distribution. So this, again, is just for the sake of saying what the function is. You don't have to memorize it. RStudio is going to work with this function directly to numerically integrate. But right here, when we're using RStudio to get a p-value out, that highlighted portion right there, that's the only syntax we would ever need. So this gives the syntax for the p-value. All we need to know is what goes in place of A. We'll already know what K minus 1 is, and lower dot tail will be set to false on every single hypothesis test. So this test goes a little bit different from the others we've seen before. Here we're going to do what we are going to describe as an overall test for a difference in the population proportions. So we've got a function here. The most informative thing is the role K plays. This we're going to compute directly to get a p-value out. And just to make this more concrete, I have a plot of several probability distributions for chi-squared. This is the chi-squared if K equals 4. This would mean we have one categorical variable with 4 outcomes, which means the degrees of freedom is going to be K minus 1 for a 3. And this is the shape the curve takes. It's wildly different from what we've seen with the normal distribution and the t-distribution. This one is severely skewed to the right. And as the number of outcomes in the categorical variable increases, that skew becomes less bad. It does get more and more symmetric. Right around 10, the symmetry is a little bit better, but there's always substantial skew in the chi-square distribution. So that gives us a mental image of what's going on when you compute this up here, p chi-squared for a p-value. These are the pictures that will be in the back of your mind. Well, the next thing we're going to take a look into is just the description of the test. Then we'll look into 2 different kinds of problems. We're going to look into, is there a difference among the relationship between seasons and whatever the counts are referring to, homicides in this problem. Then we'll look into another problem where we have a specification of blood types. We're wondering if that's accurate to a particular demographic, which has these different donations for those same kinds of blood types. Both of these kind of problems are for categorical data, but more than two outcomes, and so we have to use the chi-squared procedure. The problem will ask us for the parameters, very similar to what we just did, but the null and alternative hypotheses, that step goes a little bit different. So that's what we're going to focus on next. What are the actual null and alternative hypotheses for the chi-square test? That takes us to this part of the notes. First, the definition is just a reminder of the setting that we're in. We're considering one categorical variable, just a single one, that's having more than two outcomes. K is the number of those possible outcomes at 3 or higher. And we are not going to call the outcome successes failures any longer because there's 3. There's a trichotomy at minimum or even more. Next thing we're going to do, let me add just a little bit of space here. Next thing we're going to do is define the parameters. Pi is going to be the true proportion of the outcome occurring. So if our variables are blood types, P1 might be the true population proportion that blood type A comes out. P2 might be the true population proportion that our response is blood type O, and so on. There's going to be K different values for P as we go from 1 to K, same as the number of outcomes. And after we gather a random sample of size n from this population, we measure where people fall into each one of these categories and check this null hypothesis here. So this is our standard, or let's say it differently, our general null hypothesis. Our author states this just once, but I want to state a different null hypothesis that can occur in a very specialized setting. But first, let's study what this one is saying. There's K parameters. We index them by I, as I goes from 1 through K, the number of outcomes. Here they are in the null hypothesis, P1, P2, through Pk. So K outcomes means K different parameters altogether, and we assume they take on these values. P1 naught, an assumed proportion for the first parameter, P2 naught, an assumed proportion for the second parameter, and so on. The subscripts are a little bit annoying because now they're stacked. The zeros here are just telling us we're talking about the null hypothesis directly. So that's our general null hypothesis. Any questions about it so far? Okay, another comment we can make when we look at that null hypothesis is because these are proportions and we're looking at all possibilities that a person in the sample of size n can belong to, we have this next formula. P1 naught plus P2 naught plus add all the hypothesized value up till Pk naught. That always has to be exactly 1 to refer to 100%. So with all these down, if the null hypothesis is true, this actually goes back to what we did, directly in chapter 20. We calculate the expected count, not number of successes because there are no success failure notion this time, but we calculate the expected count that outcome I occurs by taking n times Pi naught. So we'll return to this formula whenever we're computing the test statistic. So that's the generic form of the null hypothesis. But sometimes the null hypothesis takes on a different form. And so that's what we're going to describe here to the right. A specialized null hypothesis. So what's going on in this so-called specialized null hypothesis is, when you look at this one, we've assumed a specific value for every single parameter, P1, P2, P3, all the way to the last outcome of the variable, Pk. So we give these probabilities, they have to all add up to 1. But there's another way to do this. You might have just assumed all values are directly equal to each other. You might have said, assume P1 is equal to P2 is equal to P3, all the way down to the last outcome equals Pk. And that's a completely fine assumption. It actually fits in this format for H naught. But sometimes it's good to write it in a specific way whenever that occurs. Just set all of your parameters equal to each other. Now we're saying every outcome has an equally likely chance of occurring. If it has an equally likely chance of occurring, we'll call that equally likely chance P naught. So there's our P naught value, the common value for all of these. And P naught has to be exactly equal to 1 over K. It comes from this format, actually. If you put P naught into every single one of these spots, you would have K times P naught, divide by K, and that's the common proportion. So if there's just, say, 3 outcomes, and we're assuming they're all equal to each other, they would all be equal to 1/3 in that spot there. So that's our specialized null hypothesis. This is checking for a deviation in any one of these equations breaking. And this is doing the same, but for very specific preset probabilities that we define through the context of the problem. So depending on what the problem asks us to do, we have to know if we're doing this, setting all parameters equal to each other, or doing this. We'll know we're doing this one because the problem will provide those probabilities to us. Okay, well, that's the null hypothesis. The alternative hypothesis is that Pi is not equal to Pi naught for some I. That means at least one I. There's K values for I altogether, for the first category all the way to the last. And if the null hypothesis is false, it means at least one of these equations has failed. And that's what the alternative hypothesis is saying. The proportion is not equal for at least one parameter. It also includes the case if we say at least one, or for some I, that maybe 2 of the equations are false, or 3, or maybe all of them at the same exact time. So there are many reasons the null hypothesis can be false. It could be because at least one equation fails, 2, 3, 4, or all K equations is untrue. Every single one of them could be false. So the alternative hypothesis is pretty strange. It's written this way, Pi not equal to Pi naught for some I, but don't forget to say this part right here. That part is required and important to really convey what the alternative is trying to say. Well, so far that's the test. It feels very different going from chapter 19, 2 outcomes, to suddenly chapter 21 with 3 or more outcomes. Our hypotheses start to look a lot different, but we're following the same kind of logic. It's just more parameters really on the table. Sometimes what we call this test is an overall test for any difference whatsoever. And notice, in a certain sense, this is always, no matter what, a two-tailed test in a certain sense. It's always not equal right there. We're never going to put a less than symbol there or a greater than. It'll always be not equals for some I in the alternative, no matter what. And the p-value will always look like this, no matter what. Really, the only thing that can change in format is, will your null hypothesis look like the one on the left, the general form, or will it look like the one on the right, the specialized form? Well, that's the statement of the test so far. What we're going to look into next is conditions, how to compute the test statistic, and then we'll run it through a particular problem. Any questions or comments at the moment? Okay, well, as far as conditions go on this, There are three main conditions that we're going to check. In the reading, there's other conditions being mentioned. The multinomial setting must be satisfied. But for all the problems that we'll discuss in this course, it'll automatically satisfy that condition. The multinomial setting is telling us that the probabilities given have to sum to 1, that if we have a categorical variable of k outcomes, every person in the sample has to fall into one of those k different outcomes. But that's our intention always when we define our categorical variable, and those outcomes have to be mutually exclusive. Once again, the moment we define a categorical variable, that's always our intention, that there's no overlap between categories whatsoever. These are the three main conditions that we're going to check. The first one we'll briefly discuss. And it's an important condition to discuss because what you're trying to convince yourself is you're really doing the chapter 21 procedure. We really belong here. That's really more than two outcomes, that it's not one of these prior chapters that you're analyzing. So condition 1 is just making sure you're falling into the right statistical procedure. And condition 2 is determining if our sample size is large enough. No more than 20% of the expected counts, that's through this formula we see up here, can be less than 5. And every single one of our expected counts has to be at 1 or greater. So if we ever form a hypothesis test and one of our expected counts happens to be through this formula, say 0.25, our sample size is way too small. And if many categories, more than 20% of our categories, are less than 5, again, our sample size is too small to fit the procedure. So here we will carefully check and show counts. So those are the conditions of our overall hypothesis test. After that, here's our chi-squared test statistic. That uppercase X right there is really the Greek letter chi, but since it's uppercase, it looks like an ordinary variable X. As far as the formatting goes, it does look a little bit different than X itself. If you put in an uppercase X, that's what it would look like. If you throw in an uppercase chi, you know what? It looks exactly the same. I take that back, they look identical. If you put in a lowercase chi, that's the one that goes a little bit down lined, just a slight amount, and it has that slightly cursive italicized look to it. So that's just lowercase chi. Our test statistic is uppercase chi. I guess that's the same as the uppercase letter X in our alphabet. What chi-square does is we first assume the null hypothesis is true. We'll have the counts that we observed in the data. But if we assume the null hypothesis is true, we have other kinds of counts. Those are the expected counts altogether. So we calculate this formula. How far is an observed count in category I away from the expected count squared divided by the expected count? In expanded form, this is what it would look like for the k outcomes of our categorical variable. And what this variable measures is the distance between the data and expected counts. It's a form of distance, and in a certain sense, it might look a little bit familiar to you. If we go all the way back to, say, around, I think this is week 1 or 2 of the entire class, we did another kind of distance pretty much like that went like this. When we calculate data, we want to know the difference that all the data is from its center, the sample mean. This is what it looked like, and we called that the variance before taking the square root. It was all divided by n-1. Here we're dividing by expected counts. X1 is the data. Observed 1 is our actual counts for category 1. X bar is just the center of the data, the sample's mean. Expected, well, that's the expected counts if the null hypothesis is true. We divide by the expected count as well, taking the place of the sample size n-1. So it is different than the variance for sure, but they have the same kind of goal that they're trying to achieve, these same statistics. S squared was saying how spread out the data was, measuring how far apart observations are from the center in terms of squared distances. And chi-squared is doing something extremely analogous, looking how far away our data is from expected counts, assuming our null hypothesis, whether it's this one or this one, is true. Well, any questions so far, folks, with our test statistic? Okay, as far as the test statistic goes, once we have this computed, our work is essentially over. The p-value is the probability that chi-squared k-1, that's just the symbol for the probability distribution, is greater than our test statistic, that uppercase chi-squared. We use p chi-squared like we showed on the first page of the notes at k-1, one less outcome. Lower dot tail is false, and that gives us our p-value. So really, the hard work of doing this problem is mostly what's going on with the null hypothesis. The alternative hypothesis always looks about the same. As far as calculating the test statistic, it's not too bad. It's just a number crunch. And in fact, RStudio is pretty good at doing it itself. Well, we have just a little bit of time. Let's take a look into a problem with not the goal of trying to run right to the last minute and get too far on it, racing through, but just see how this problem fits into this procedure. So here's our example one for chi-squared. We have a data table with 4 different columns and 1 overall row for counts and nothing more. The context says, criminologists have long debated whether there is a relationship between weather conditions and the incidence of violent crime. This one turns out to be real data from 1988, from a while ago. It says the author of the article, "Is there a season for homicide?" classified 1,361 homicides. There's our sample size. According to the season, resulting in the accompanying data. This is really, really short context. It doesn't really say much about this problem. I believe if you're really curious and you read that article there, you never have to for this class. I think this was for one specific city or metropolitan area in one particular year. So that's what they did. They looked at the season they were in, which is telling us about what the temperature is, and how many violent crimes, which were specifically homicides, that resulted in every one of those seasons. Now, if we look at those counts, they're all just about the same, except there's a small, minute bump right at summer for some apparent reason. So they want to know, is there something going on in these data? Was that just randomness that occurred, or is there real statistical significance of some effect in this problem? So that's the setup so far. The question for the problem says, can we conclude from the sample data that there is a relationship between season and homicide? We'll take a step back from it and say what we definitely know for sure. These data are not quantitative. Just because there are numbers here does not mean they're quantitative whatsoever. These are counts. The sample was 1,361 homicides, and all we did with those 1,361 observations was categorize them according to these 4 different categories. So for this problem, there is one categorical variable with k equals 4, one category for each one of the season categories. This is why this problem becomes a chi-squared procedure altogether. Again, there's no successes and failures. There's 4 particular outcomes this time, not specifically 2. So if there are 4 categories, that means there's 4 parameters this time that we're looking into. We want to know if there's some kind of difference between. This one we're going to give a complete analysis for. And as far as a practical question goes, this is really this question right here. Let's go with this strategy like we mentioned before. Whenever you're doing a complete analysis following this 4-step procedure from state all the way to conclude, if you like, you can put the statement part in your own words, or you can directly cite the problem. This time, let's just cite the problem. This is a great way to say what the practical question is already. So there it is. Is there some relationship between seasons and the incidence of homicide? Kind of looks like there is with that blip there, but that's not good enough just to say there's a higher count. We want to know if that's high enough for true statistical significance. In order to do that, we need to say exactly what our hypotheses are. But before we even get to the level of the hypotheses, we must know what the parameters are in the very first place. So let's cite this part of the notes here to show how we're putting this all together. It's again a very different kind of landscape for the null and alternative hypothesis in this question. So what we're defining is the P1, P through PK. So let's start by saying let P1, P2, P3, and K is 4 on this one, so P4, it's going to be a true proportion of something. The something thing is a homicide occurring according to one of those 4 categories, one of those seasons. So we have to mention what the categorical variable is all about, classifying homicides. Let P1, P2, P3, and P4 denote the true proportion of all homicides in this area. When I say in this area, what I'm meaning is this real world data here, this study was looking into one particular region, city, or metropolitan area, not necessarily national data, or definitely not global data. So we're thinking about one particular area, and we wanted the true proportion of homicides in this, all homicides in this area that occur in these categories: winter, spring, summer, and fall, respectively. So that's our new landscape for the parameters. 4 at once, even though there's one variable that doesn't tell you the number of parameters whatsoever, how many variables you're looking into. It depends on the kind of statistical analysis you're giving in the first place. What we need to do next is form the hypotheses, both the null and the alternative. And it turns out through these data, we're in the specialized case. We have one specific kind of null hypothesis. So we're going to write it out like this. But instead of racing through that in the 2 minutes of time we have, I think this is a natural stopping point. We've analyzed the context. We've done nothing too different from chapters 19 or 20. We've indicated the parameters. And when we come back exactly a week away from today, after getting through exam 3, we'll revisit the notes, refresh what's going on with forming these hypotheses, and work them out a little bit more careful without rushing through it. So this is where we'll stop for today. Any last questions or thoughts at all, folks, before we call it a night? Okay, well, thanks for your hard work in this course so far. We're getting through our last exam that's going to be an official exam in class or in a testing center. The final exam will be a take-home. If you're working on this exam over the weekend on Friday, I'll be trying to grade any homework sets on these chapters as soon as possible and addressing any questions you have. I'll be checking my email primarily in the early parts of the day. So even if you send me an email late at night on, say, Saturday, I'll get back to you on Sunday. But have a great afternoon, folks. I'll see you all next week after the exam if you're in the online section. Take care.
So I had a question regarding the homework and I was wondering if you could take a look at it.
Yeah, I'd be happy to help. Absolutely. Which homework were you looking
Thank
into?
you.